Open channel flow is also called free surface flow, and it is definitely gravity driven. For example, a free surface flow could be a river, a man-made canal, or pipelines when the pipe is not completely full of water. For open channels, uniform flow means that the depth and cross-section remain constant. The uniform flow depth is referred to as normal depth, and we represent that with an I subscript N. So if we've got our little spillway here, we're going to have uniform depth coming to the spillway, but when it first hits the spillway, it's going to get non-uniform. And then as it goes over the spillway, it eventually gets back to uniform. And then it hits the bottom of the spillway back to non-uniform. And then eventually as it goes down in our new channel or river, it'll get uniform again. The important pi groups for open channel flow are Froude number, which is velocity divided by gravity and length, and Reynolds number. Now you may notice the Reynolds number looks a little bit different than what we were doing with the pipes. It's still hydraulic radius. Hydraulic radius for a pipe is the diameter, but for an open channel, the hydraulic radius is the area of the cross-section divided by the wetted perimeter. So if this is my cross-sectional view of my open channel full of water, this would be my cross-sectional area. And these three sides where the water is touching the channel sides, that's the wetted perimeter. For open channel flow, laminar flow is usually less than 500 for the Reynolds number. For turbulent flow, the Reynolds number is going to be around greater than or equal to 500. I put 500. It's really around 750, but pretty much anything over 500 we assume is turbulent. And for open channel flow, most of the time it's going to be turbulent flow. So let's say we've got water at 70 degrees Fahrenheit flowing through a 6-foot wide rectangular channel at a depth of 3 feet. What at a mean velocity of 0.1 foot per second? What is the Reynolds number for this setup? For our Reynolds number calculation, we need the velocity times the hydraulic radius all over the kinematic viscosity, or the density velocity hydraulic radius over dynamic viscosity. So the hydraulic radius is equal to the area divided by the perimeter. So our area is the entire cross-sectional area of our system. So that is going to be 3 feet by 6 feet. The wetted perimeter is only the sides that it's touching in the open channel. So I've got 3 sides here. So I have 3 feet plus 6 feet plus 3 feet. My calculations are a hydraulic radius of 1.5 feet, which means my Reynolds number is going to be the velocity of 0.1 feet per second times 1.5 feet, and then looking up the kinematic viscosity in the back of the book, I get 1.06 times 10 to the negative fifth feet squared per second, which is equal to 14,150 for my Reynolds number. This is far greater than 500. This is definitely turbulent flow. So what depth would we need for it to be laminar? Well, that's going to be setting a Reynolds number equal to 500, same velocity, and hydraulic radius is what we're looking for, same water. And we find a hydraulic radius of 0.053 feet. And that's going to equal to the width, 6 feet, times the depth that we're looking for, all over 2 times the depth plus 6 feet. And we find that the depth we need is 0.052 feet or 0.62 inches. Very, 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 very shallow, which is why you can see that most of the time open channel flow is turbulent. Steady uniform flow is where velocity is constant, as well as the cross section. So if I'm looking at a side view of an open channel, I'm going to have the channel bed slope. So this is the slope over my distance x, where distance x is any portion of the open channel I'm looking at. And we're going to have down here our elevation 2, and up here our elevation 1. And then, of course, we have the water of the open channel flowing over it. Where at elevation 1, we're going to have some sort of depth here, depth 1. And then over here at elevation 2, we can have a change of depth here. By the way, this water surface is the hydraulic grade line. Remember, that's where the water wants to be when open to the air. Open channels are open to the air, which means there's going to be an energy grade line. And that change of the energy grade line from point 1 to point 2 is our head loss. Remember that the distance between the hydraulic grade line and the energy grade line, tiny little distance right there, is our velocity head. So we've got a couple of different slopes here. First is the bed slope, or that green surface slope, and that's the change in elevation over the length x. Then we have the hydraulic grade line, or the water surface slope. That's going to be the elevation and the water depth, that change over the distance x. And then last we have the energy grade line slope, which is the head loss over the distance x. For steady uniform flow, the cross section remains the same, which means the depth remains the same, which means the water slope, or the hydraulic grade line slope, is the same as the bed slope. So that means the entire energy mess is going to be controlled by the head loss. Taking this head loss equation and replacing it with the slope equation for the energy grade line, which is head loss over the change in x or length, I can combine these two and get a velocity equation, which is 8 times gravity divided by the friction factor times the hydraulic radius times the slope. We're going to take the square root of that quantity. Putting this into practice, let's say we have a rectangular concrete channel that's 10 feet by 6 feet with a cross-sectional area of flow, and it has a slope of 0.0016. Find the flow rate. Remember that flow rate, Q, is equal to V times A. We already have the cross-sectional area. That's going to be 10 feet by 6 feet. That's going to be 60 feet squared. And then velocity we can solve with our equation. 8g divided by F, hydraulic radius, times the slope. Slope we were given. Hydraulic radius is going to equal to the area divided by the wetted perimeter. So that's 60 feet squared divided by 2 times 6 feet plus 10 feet. And that gives us a hydraulic radius of 2.73 feet. Gravity is a constant, and then we have the friction factor. We can get the friction factor the same way we did for pipes. Now, like I said earlier, we assume turbulent flow, so that would give us a minimum Reynolds number of about 750. The roughness factor we can pull from our pipe tables. And for concrete, we have anywhere between 0.001 and 0.01 feet. So let's just say we have really rough pipe and use 0.1 feet. D again is that hydraulic radius, because I pulled the equation directly from the pipes. The pipe is D for diameter for the hydraulic radius, but this is an open channel. So plugging everything in, I get a friction factor of 0.075. Plugging that into my velocity equation, I calculate a velocity of 3.873 feet per second. Now that I have a velocity, I can calculate my actual Reynolds number. And I was not given a water temperature, so I just assumed standard water temperature, which is about 1.2 times 10 to the negative 5. And I get a Reynolds number of 881,107. So with that new Reynolds number, I'm going to iterate again. And plugging that into my friction equation, I get a friction factor of 0.016. Which gets me to a velocity of 8.39. Which gets me to a Reynolds number of 1,907,815. So then I again iterate, and plugging that Reynolds number into my friction factor, I get a friction factor of 0.016. And that is the same as we got last time. So convergence, yay! So we're going to use the velocity of 8.39 feet per second with our area of 60 feet squared, and we get a flow rate of 503 cubic feet per second. One common method for solving open channel flow is Mannings equation. If you're using SI units, flow rate in Mannings equation is going to be 1 over n times area of the cross section times the hydraulic radius to the 2/3 power times the square root of the slope and if we're using US units, that numerator is going to change to 1.0 486 over n, area of the cross section, hydraulic radius to the 2/3, and bed slope to the 1/2. You can find the roughness factors from table 12.1. If we have a 100-foot wide, 4.3-foot deep rectangular channel with a slope of 3/1000 and a friction factor of 0.13, find the discharge and the roughness coefficient. Okay, so above Manning's equation, discharge is equal to 1.486 over n times the area times the hydraulic radius to the 2/3 times the slope to the 1/2. We are looking for two variables in this equation, discharge and the roughness coefficient. So we're going to have to do a little bit of work, but we can find the area, which is 100 feet times 4.3 feet. So that is equal to 430 feet squared. And my hydraulic radius is going to be that area, 430 feet squared, divided by 2 times 4.3 feet, plus 100 feet. And that gives us 3.95 feet. And the slope we were given, so we're almost the way there, so we need Q. Remember, Q is equal to velocity times area for an incompressible fluid, that's what we're assuming here, it's water. And our velocity equation we talked about earlier is 8g all over the friction factor, hydraulic radius, slope. So that's going to be 8 times 32.2 feet per second squared all over the friction factor that was given to us at 0.13 times the hydraulic radius, 3.9595 feet, and then times that slope. And we calculate a velocity of 3.96 feet per second, meaning our flow rate is 3.96 feet per second times 430 feet squared. Q is equal to 1,700 cubic feet per second. Now that we have Q, I can plug it in back up here and solve for Manning's coefficient to be 0.052. What if we have a channel that is not rectangular, like this one here, where we've got this rectangular portion, but then it angles out to the side? The entire depth of the channel is 2 meters, but right now it's only running at 1.5 meter depth. The rectangular portion is 4 meters across and the entire channel is 20 meters across. We're given a flow rate of 25 meters cubed per second and a Manning's roughness factor of 0.016. Find the required bed slope to maintain this flow rate. All right, we're in metric, so our Q is going to be 1 divided by n times area times the hydraulic radius, 2/3, and the bed slope to the 1/2. To find the area, I need to know this width here. I can find it with similar triangles. I know that this portion is going to be 16 meters. And it is acting 1 meter depth. And my portion here is acting at a 1/2 meter depth. 1 meter over 16 meters is equal to 1/2 meter over the width. So the width that we are in our angled portion is 8 meters. My area is going to be 1.5 meters times 4 meters plus 1/2 of 8 meters times 1/2 meter. And that gives me an area of 8 meters squared. My perimeter, wetted perimeter, is going to be 1.5 meters plus 4 meters plus 1 meter plus the square root of 1/2 plus 8 meters. And that gives me a wetted perimeter of about 14.52 meters, which means that my hydraulic radius is 8 meters squared divided by 14.52 meters. And that gives me 0.5511 meters. Everything else I already have solved, therefore, are given. 25 meters cubed per second is equal to 1 divided by 0.016 times the hydraulic radius, 5511 meters to the 2/3 times the slope to the 1/2. Oh, I forgot my area, 8 meters squared. Solving for slope, I get 0.00553 in 3 significant digits. So I've been giving you cross sections up to this point, but what's the best hydraulic cross section? The best hydraulic cross section is where the largest area for a given perimeter, because we want that maximum hydraulic radius, right? A semicircle, of course, is the best hydraulically, but it's kind of expensive to make. Your depth of flow Y, that's going to be your optimal depth, ends up being the diameter divided by 2, or the radius. If we square up everything on a semicircle, what we're going to get is a trapezoid. So this is the next best option. And if I have the sloped sides at an angle theta from the horizontal and a base width b, my optimal depth is going to be b times the sine of theta all over 2 times 1 minus the cosine of theta. If we continue to flatten it out, we're going to get a rectangular channel, and our optimum depth is going to be base divided by 2. So let's say we have a finished concrete canal to carry a flow rate of 1.5 meters cubed per second at a slope of 0.00085. Find the best hydraulic cross section if it's rectangular. This is metric. Our Mannings equation is going to be 1 over n times the area and the hydraulic radius to the 2/3 and the slope to the 1/2. My n I can get from table 12.1, and it is 0.012. My area is going to be base times height, and we know that the optimum height for a rectangle, y is b divided by 2. So if I plug that back in here, my area then becomes b squared divided by 2. My wetted perimeter is going to be 2y plus b, again plugging in that optimum height. I have 2 times b divided by 2 plus b. So my wetted perimeter is 2b. Plugging that into my hydraulic radius, I have b squared over 2 divided by 2b, and that gives me a hydraulic radius of b divided by 4. I have a flow rate, a slope, an area, and a hydraulic radius. So let's plug it all in. 1.5 meters cubed per second is equal to 1 divided by 0.012 times my area, b squared divided by 2, times my hydraulic radius, b divided by 4 to the 2/3, times my slope, 0.00085 to the 1/2. And working it all out for b, I get about 1.18 meters, meaning my y is going to be 0.59 meters.